Thank you. Let's get on with it. So we all know that the Python standard library is pretty stable and we'll like it. However, in the last 3 years, there were 2 packages that got massive evolution. The first one is typing, of course, and the second one, you guessed it. Async.io is the Python implementation of asynchronous programming. It's a fairly new concept in the Python ecosystem. The first stable implementation of async.io was introduced in the standard library in Python 3.5. That's 2015, so more or less 8 years ago. However, in 8 years, async.io has become the backbone of all the most popular frameworks out there. FastAPI, Django, you name it, they're all based on asynchronous programming. Asynchronous programming is a set of primitives to fake parallelism, getting the advantages of parallelism without using multiple threads or multiple cores. That is, all of the fun without edges. That would be great, but there is also the other side of the medal, of course. I think that the core of async.io and asynchronous programming overall can be summed up with waiting smart. It's nothing more than a smart way of handling waiting time. Why is waiting time a big deal with modern hardware? Well, let's play a game. Let's say that one CPU cycle does not last fraction of a nanosecond as it does in the reality, but it lasts 1 second just to get closer to the human timescale. Then if a CPU cycle lasts 1 second, fetching some data from the L1 cache, the fastest memory out there, takes 3 seconds, 3 CPU cycles. Going to the random access memory, the main memory of the system, it's in the order of minutes, 4 minutes, let's say. Fetching some data from the network that is completing a request-response HTTP cycle is 7.6 years. So we are talking seconds against years. It's like the time you spend asking something from the Italian public administration and getting the answer back. It's the same time scale. So the point is, you do not want to wait years for something that can last just seconds. Very good. In the next 20 minutes, I will try, 17. I will try to first introduce you to some basic ideas: concurrency, parallelism, threading, processing, multiprocessing, sorry, and asynchronous programming. With that out of the way, I will try to show you some basic examples to see how async.io works. And then we will try to go a little bit deeper, untangling the processes below async.io, trying to see how it really works on a lower level. We will conclude by discussing a little bit when to use async.io, how to use it, what are the main pitfalls of this style of programming. But an hitchhiker, should start somewhere. What better place with a lot of movement, lots of cars than, oops, my bad. Good. Than a McDonald's. You see, a McDonald's works a little bit like this. You go there, there is just one waiter, you give your order, the waiter passes the order to the kitchen, and then serves the next customer taking the order, the next customer taking the order. When a meal is ready, the waiter gets the meal from the kitchen and he delivers it to the customer that has requested it. That's a smart way of waiting, because it's not waiting at all. He's just performing the fast operation, handing over the task to another actor, which is way slower than him. I'm just using the male adjective, but I mean, I don't think that anyone gets offended for the McDonald's. And then, when the result is ready, he takes over again. So it's a way of avoiding to wait without parallelizing the work. Compare that to a post office. If you go to a post office, you have plenty of clerks waiting for customers to serve. Once you go to a clerk which is free, then the clerk is yours. If you have to fill a form, you stay there, basically wasting the clerk's time, and fill a form in front of him. Then, when you're done, you hand over the form, and the clerk can serve another customer. That's real parallelism. You have multiple resources doing the job. In the McDonald's, you don't. You see the difference? OK, let's get out of the metaphor, and let's go to real computer science terminology. In Python, you have 3 ways of achieving or faking parallelism. Let's discuss immediately about about the only way of achieving real parallelism in Python, and that's using multiprocessing. Multiprocessing spawns different processes, each of them with its own interpreter. So it's basically different copies, different Python interpreters that run in parallel on different CPU cores. Is it good? Is it bad? Well, it's great. It's real parallelism. You're using multiple computational resources. However, that's very heavy. Spawning a process for each task that you're going to perform requires a lot of overhead. And multiprocess communication is difficult. So when do you want to use it? When you have computationally intensive tasks that really take advantage of having multiple computational resources allocated to them. You don't want to have 3, 6, 16 Python interpreters wasting the time of your course staying idle and waiting for something external to happen. Very good. Second one is threading. Threading means that you're creating multiple tasks that are assigned, each of them, to a specific thread. Threads are operating system objects. That is, they're executed on the different cores as the operating system wants. So the point is that you don't know when a task will be executing on the core. The operating system does the job. It can start the task, it can end the task, it can pause the task. You don't have control. Python has the infamous global interpreter lock. It means that the Python interpreter can run only on one core, one and only one. That means that you can have 1,000 threads, not a great idea, but you can have 1,000 threads, but they will run all on the same core, and they will be handled by the operating system. asyncio implements a different paradigm. It implements cooperative multitasking. It gives you, the developer, the ability to suspend and resume tasks. Again, it uses just one thread, just one core. But it's much more, it's much better for I/O-bound applications. That is, assume you want to call an HTTP API. It's very fast to perform the request. Then you have to wait. And then it's also very fast to process the response. What you want is to free the computational resources while the network is performing the operation and you're waiting for the response to come. And that's exactly where asyncio comes handy. So now there is the live coding part. So this is the classic hello world with asyncio. We need to note a few things here. First one is that we are not defining a main function. We are defining a main coroutine. You see async def. Coroutines are just like functions, but they have the ability that functions do not have to stop and resume the execution. They're more or less like generators. Actually, they are built on top of generators in Python. And that's their advantages. They have advantage over normal functions. Inside a coroutine, and all inside a coroutine, you can use the await keyword. The await keyword is basically, look, now I'm going to perform an operation which may require a long wait. So just put a flag here, give the CPU away to someone else that must do some work, and then come back here, awaken me when the data that I need are available. So the other thing that we must note is that we're not calling the main function as we would in a normal synchronous code, but we are running asyncio.run. Asyncio.run is the top level executor for asynchronous code. If you enter asyncio.run and you inspect the code, you would see something like this. Well, a well-engineered version of this. What we are doing is using a very important object that is the Python event loop to run the asynchronous code. The event loop is the only object in Python that is allowed, that is capable of running asynchronous code. That is, it's the only object that can understand async and await. I need to skip something. I will skip this one. So let's see something useful. Let's try to use concurrency to speed up this kind of operation. So here we are just mocking some long-lasting operation, send crow. Let's say I'm a fan of Game of Thrones, that's why send crow. But apart of that, the idea is that send crowd is maybe a call to an HTTP service that returns the response after 1 second. Note that I'm not using the usual sleep function of Python, but I'm using the asynchronous asyncio.sleep. We will see how it works in a moment. Then I'm using asyncio.gather for the free to run the free asynchronous operations. The idea is that if this code was executed synchronously, it would send the first crow, wait 1 second, get the crow back. Then send the second crow, wait 1 second, get the crow back, and so on. So total elapsed time, 3 seconds. Let's say 3.001 for the sake of the argument. And out of the 3.001 seconds of elapsed time, then exactly 3 seconds are wasted because the CPU is sitting there doing nothing. What we want to do is to send the first crow, send the second one, send the third one, and then wait for the first one to come back, the second one to come back, and the third one to come back. That's smarter. That's the McDonald's waiter. And that's exactly what happens here. If I run the right script, that is. Right? So total elapsed time, 1.001 second. That is 1 second wasted waiting and 0.001 used in performing operation on the CPU. Okay, so we understand that asyncio.gather makes some magic. We understand that this async await stuff should do something, but what is it doing? Okay, I'm not making the mistake of putting this full screen again. Let's go with this. What is happening is this thing here. That's very important to understand how asyncio works. That's the important slide. What happens is you run in a single thread. You run in the event loop. When in an asynchronous function you call await, what happens is I'm trying to handling some input-output operation. That is, I'm trying to reading or writing into some socket. I mean the operating system socket, not the network socket, right? So I'm going to perform both the operations. So let's say that I want to call an HTTP service. I'm trying to do the request, and that's fast. But then I'm also trying to read from the socket that should contain the response. And that's not going to happen because the response is not there. But I try to do anyway immediately. okay? So when the event loop understands that the code is trying to perform an operation from a socket that is not ready, what it does is taking note of the coroutine that is trying to perform the operation and the socket that it is trying to read or write. Just takes notes, okay? Then it leaves the coroutine there, interrupts the execution, that's the await, and goes to the task queue. So it tries to look for another coroutine that is ready to be executed. It finds one. That's the second send crow. The story repeats. It goes to the point where the coroutine gets interrupted, and it takes note. Now you have a mapping with two coroutines assigned to two different sockets, right? You get a third one. And then you run out of task to run. What the event loop does there is to call the select system call. The select system call, basically, it's a blocking call. So now the CPU is really idle, waiting for something. But what it's waiting for is a signal from the operating system. So it has handed over the control to the operating system. And the operating system is going to wake up the event loop when either of the freeze and crow completes. So when one of the three sockets that we are trying to read if we were calling a web service is available, then the event loop gets woken up by the operating system. And then it resumes the execution of the code sequentially from the await, right? Then again, it completes the task. It tries to find another task to execute. Is it there? No. Call the select system call and hand over the control to the operating system. The operating system will wake you up, and again and again and again. Okay? You see the magic. There is no stochastic behavior there. The code is always executed sequentially. The only thing for which you're handing over the control to the operating system is to wake you up when the data is available. So you're not, you don't have to handle thread communication. You don't have to handle all these weird errors and bugs that come up with threading and so on. It's much simpler. It's all about waiting in a smart way. However, if you make the mistake of scheduling in the event loop a long-lasting coroutine, that is a coroutine which is not I/O bound, which has not to wait up until some data becomes available, but is maybe, I don't know, performing a mathematical optimization, so a very CPU-heavy task, that coroutine will never get suspended. So the task will keep populating the task queue, and your application will basically be stuck. That's why in FastAPI you should use background tasks for long-lasting operations and don't do it in asynchronous coroutines that implement the APIs. Very good.
Can I ask a short question? Can you give it back?
Sorry?
Can you give it back to the event tool for long-lasting tasks?
No. No, you can't.
Slide, please.
Okay? So what I would like to do in the last 2 minutes that I have is to try and show you a real example where async I/O is useful. So what we want to do here is to perform multiple HTTP requests using concurrency. So we want that at any given time, just 3 requests are on the network. Why? Because we don't want to perform a denial of service attack against HTTP bin. So we use a semaphore. semaphore. A semaphore is a primitive, like a threading semaphore, it's the same thing, that limits the amounts of concurrent code that can execute at the same time. What we are doing here is creating 20 tasks, right? Tasks are just wrappers of coroutines, so are objects that can be awaited. We are not awaiting anything because from Python 3.11, the task group automatically awaits all the tasks that you create with the task group itself when the context manager gets into the asynchronous exit method. So at line 22, let's say, we will await all the 20 tasks. But remember, we have a semaphore with maximum concurrency 3, so only 3 coroutines will be executed by the event loop at any given time. Then what we will do is just wait for everything to complete, and that's done by the asynchronous exit method of the task group at line 22. We will check the exception, we will check the cancellation, and then we will print the results. They are just sequential integers, so that's a very complex way of computing a sum of the first 20 natural numbers. I don't have the heart of running this, but I will tell you that it's on GitHub and it works. Trust me, I'm an engineer. With that being said, questions, please.
Thank you, Emanuele. Thank you, Emanuele. Well, there is one question. For now, I will just read it. How should Python solve the sync/async function caller problem in a future language version? I don't know exactly what function caller mean, but if there is people who ask the question, maybe you can clarify a bit.
I mean, I would say that the problem of distinguishing synchronous code and asynchronous code is already solved. Asynchronous code is implemented by the coroutines that you define with async def, and it's the only, they're the only piece of code that can have a wait inside them. So that's the distinction.
Okay, so I think we can have 1 minute more if you want to, if anybody's okay.
Are there many different event executors? Like, I think there are different ways of managing the queue, if you can tell some differences.
Yes, there are. So first, Python has 2 default implementations of the event loop. One that is working only on Windows, and one that is working on every operating system, and the second one is the one you get by default when you use asyncio.run. But you can write your own event loop if you really want. You can write your own event loop, but I would not do that. For the executors, let's say that the most interesting stuff that you can do is to use the thread pool executor. That is not asynchronous programming, but it is threading. So under the hood, even though it is made available also in the asyncio library, what it does is actually creating threads to run your code. That's usually what you do when you want to run long-lasting computations, because threads are preemptive and are managed by the operating system. So if a thread gets the control of the CPU and wants to run longer, the operating system just says no.
Okay, thank you, Emanuele. I'm very sorry for all the